All right, so let's start off talking about this star-nosed mole. This conversation about evolution, we're going to talk about with the star-nosed mole. This star-nosed mole has tentacles and stuff like this that are used to smell the air. Right? They almost like taste the air more than smell the air. So we're going to look at this organism, hunt worms. That's what it eats. It eats worms. So we're going to watch it hunt worms. It's a worm hunter. So here we have the star nose. It's tasting the ground. By tasting the ground, it can actually tell, the worm's this way, the worm's this way, the worm's this way. There's the worm. And now, full speed ahead, we're going to go ahead and eat the worm. And you can see it like literally gobble the sucker up faster than you would expect a blind mole to be able to do. But yet, here we go. And it's well adapted for this underground dark living where you can't really see anything and you can't really appreciate anything there. And that's the star-nosed mole. And the star-nosed mole is going to be explained a little bit with the idea of evolution. So evolution is a change in the biology of an organism. It's kind of neat that way. We're talking about going from ancestors to descendants, not from one generation to the next, but maybe over 100 generations or 1,000 generations. How organisms change. For example, these are bones of a horse 55 million years ago. These do not Horses do not look like this now. They look very different. And you can see like the back legs are long and the front legs are shorter. These back legs are also stronger. You can tell by the bone structure. And that's not really what horses are today. And 55 million years is many, many generations of horses. So it's not that strange that you would have very different bone structures in different organisms. When we're talking about evolution, we're going to be focusing in on species, which is a group of organisms that can make, they have a special word here, fertile offspring, which means these are organisms that can make babies, and those babies can make babies. So some of you might think of a horse and a donkey can make a mule, and that's cute, but a mule cannot make a baby. A lion and a tiger can make a liger, but a liger can't make a baby. And there's a few other examples where it's two different organisms that can make an organism, but that organism is not fertile. And that's why donkeys and horses are not one species. There are a lot of people who played a role in making of our understanding of evolution. Linnaeus was one of the ones that created the way we name organisms, right? It's a classification system and how we name and organize organisms. Buffin, uh, Buffin's idea is this idea that some organisms have a shared common ancestor. That not everything just became what it was independently of everything else. Some things are like cousins, right? So they have one shared ancestor if you go back far enough, and then they separated from there. Darwin's idea was that more complex came from less complex, and Lamarck, I like to say Lamarck had a use it or lose it sort of mentality, where if you don't use something, it kind of it becomes less and less prominent in an organism. That's not saying if you don't use it. That's saying if over the next 1,000 generations organisms don't use it, then it'll become less prominent. Uh, they also looked at how the Earth changes, right? And I want you to understand these scientists, these guys risk their lives, a lot of them, because back in the day, if you started saying nonsense like, that there was a shared ancestor between chickens and other birds or something, people might get mad at you. And that may not be all that safe for you. So I just wanted to mention that as we move forward, that these scientists sometimes risk their lives or at least risk their reputations. And it's something to bear in mind as we move forward. So when you're looking at the Earth doesn't stay the same. The Earth does change. There's catastrophism, which is when like a catastrophe happens, a volcano, hurricane, major changes to major land masses over time. Gradualism, I don't know if you're aware of this. This river used to run way up here, right? And then as the river would run in the same direction, it kept carrying away soil and dirt and stuff, and it kept carrying it to the sea or whatever, making this big gorge. And uniformitarianism. You see how there's a banding pattern here? Red, what is that? Gray, red, black, orange. You can find the same like banding pattern, the same pattern of colors all over the world, because dust all over the world is being mixed with air currents. So, like, we get Arctic dust in the winter, we get African dust with hurricanes. Dust is being mixed. And then, if you look at these little bands, if you find the same pattern in Iraq and then you find the same pattern in Utah, let's say, then that means that this dirt was settled at the same time, which is kind of neat that you can actually compare time frames even if you're on different parts of the world. And it's just this idea that in uniformitarianism, that each layer is going to be layered down from the dust, and these dust colors actually represent what's going on Earth. You're like, oh, well, what do you mean? Well, if there's a lot of volcanoes, maybe there's more ash in the air. So these might be periods, millions of years of increased volcanic activity. Maybe here there's less volcanic activity. When oxygen started to first become prominent, you would see a banding pattern that's special in the rocks then. So you can see changes in the earth in these patterns. And that is the end of chapter 10, section 1.